Hi everybody, hope this video finds you all well. We're almost done with the restoration of our Lafayette LR441 receiver, and the very last part that we're going to do deals with the quadraphonic section, which in this one is a matrix based stereo quadraphonic, and we'll talk about quad in another video. But in order to do that, I wanted to test out the phono stage on the amplifier, and strangely enough, when we look at the schematic for this thing, they don't really show you much about the phono stage in this thing. And you can see there's a little bit here they show, but nothing about the quadraphonic, nothing about the matrix decoding circuit. So this thing can do SQ, and it can do two different types of other matrix called Composer 1 and Composer 2. And there's no schematics, and there is no documentation in the service manual for that. But neither here nor there, I want to be able to test out my phono stage. Now, some of you have seen this little thing that I used, and I purchased it from Hagerman Audio Labs, and you can just go to that hagermanaudiolabs.com and you can order one of these. I've had it for a while. But really what I want to do is, I was perusing eBay one day, and this was probably about a year or two ago. This is how long. And I came across these things. Now, I don't even know if they're still available. What I will do is, if I can find them on eBay, I will try to screen capture the site, on eBay, and kind of post an image of it up on the screen here while we're talking. But what this is a little kit called an inverse RIAA converter. So what it does is it removes the RIAA curve from your phono stage. Now, what the heck is all of that all about, you might ask. So some of you who are new to the vinyl or records hobby probably haven't heard some of these terms. Some of you are probably more familiar with them than I am. So the whole thing about RIAA equalization curves, what does it all mean? So to understand what RIAA equalization means and why you need it and all that sort of stuff, let's go all the way back to the beginning and look at an actual record. So I have a standard 33 1/3 record here in front of you. And if you look at it very closely, and we'll do that here in a minute, you'll notice all these little grooves in here. And people say, I'll ask somebody, how many grooves are in that record? And people who don't really know, it's kind of a little joke. They try to count all these little ridges. Really, there's only one groove on this side and one groove on the other side. So a standard record has two grooves, because this is a spiral cut groove. It starts on the outside and it winds its way all the way into the middle. Now, the platter that this thing sits on a record player rotates at a constant speed. Now, with this type of record, this is an LP, it rotates at 33 1/3 RPM. And you might think that's a constant speed. Well, it's a constant rotational speed, but the actual speed at which the stylus is traveling through that groove changes. Why does it change? Well, at 33 RPM, the outside portion of the record is actually covering a larger distance than the inside portion. Because remember, if you take the circumference of the outside, you're traveling that circumference 33 1/3 times each second. So you can actually measure the actual length of that. And if you take that same circumference at the inside of the record times the 33 1/3 RPM, it only travels this much distance in 133 1/3 of a second. So the actual velocity slows down as you get towards the inside of the record. Now, with that already said, okay, if we just take a certain section of this record and we measure it, there will be a pretty much constant velocity in that area. And depending on what frequency of a signal we're putting in there, it will affect what that little groove looks like. Because what's happening is you have this tiny little stylus. Let me see if I can show you one very quickly. So here is a head shell with a cartridge, and that tiny little thing in there is your stylus. That's the little arm. You have the little arm that the stylus is attached to. And there's a tiny little stylus, or a little needle they call it. But it's actually a little piece of diamond on the tip there. And that is actually passing through that groove. And as that little arm wiggles back and forth, there's a magnet and coil inside there that creates a little electromagnetic field. It puts out a little signal. And the rate at which that vibrates controls the frequency, right? So if it's warbling at 60 times per second, you get a 60 hertz tone, and so forth. The problem is, and let's take a look at the grooves, and I'll kind of show you here what one looks like. So here's a picture of the groove under my little microscope, which is not a really high-powered microscope, but you can see the grooves, and you can see they kind of look funny, right? So certain grooves are kind of grayer than others, and then you see like black spots, spaces in between. And if we go down and we take a static image of that and blow it up a little bit bigger, you can begin to see that in certain spots the grooves get wider and narrower. And you can almost start to see, see right in here, this little section, you can see the little sounds. So these little ones would be higher frequencies, and the wider ones like this would be lower frequencies. Now, keep that all in mind. All those little grooves, those little imperfections in there, those little warbles, are cut into that groove by the record cutting lathe. So a record cutting lathe is the recording device that actually puts those grooves, or puts that information into the groove of the record. I'll try to put up a picture of a record cutting lathe here so you can see it real quick. Now, if you notice, the width of those grooves were very consistent. In other words, the space from one to the next was the same the whole way across. And really, just the little widths of cut, like those little notches inside that trough, were squeezed in and out, but the entire length was the same. Now, the reason that is that way is because of the RIAA curve. And here's the thing. If we have our little cutting lathe stylus, so this is the little point, and it's going back and forth and cutting as it goes around here. That cutting tool in that record cutting lathe moves at a constant velocity, meaning this direction, it always travels the same speed, the same velocity back and forth as it's cutting this. So what does that mean? Well, if it's a lower frequency, as I travel a certain distance, this is going to travel a wider distance over that distance. So at low frequencies, like 20 hertz, the groove is going to have to be really wide because that stylus is going to travel a really wide distance based on the length of the groove that you're cutting. As the frequency goes up, you're changing directions more quickly and the groove gets narrower. The cutting path gets narrower until finally you get up to really high frequencies and it's barely moving. So what does that mean? Well, it means that lower frequencies will require a wider groove and higher frequencies will require a skinnier groove. And if that were the case, our little picture up here would not look like this. What would happen is anywhere there was a lower frequency, this groove would have a wider width, and anywhere there was a higher frequency, this groove would have a much lower width. And what that would do is that would waste a lot of the record. So the groove would look very strange. So what we're doing is we're changing the actual amplitude of that frequency at lower frequencies. So at the lower frequencies, we're putting lower amplitude so that stylus travels less distance. And at higher frequencies, we're putting a higher amplitude so that it travels more distance. And it equals out that no matter what frequency we put in there, it's always moving the same distance or similar distance within that same width of that groove, if that makes sense. It's all physics and math, really. And the reason they do that is to be more consistent with the groove. You can fit more information and make a narrower groove on your record, so that makes them play longer. And it also helps to eliminate other noise. So if you have a really wide groove and there's a lot of gunk in that wide groove, it's going to create a lot of noise. So this is also going to help a little bit with noise, but it's also going to create a few other problems. So everything's a trade-off with this. Now, what is RIAA equalization? Well, since we're using a constant velocity on this record down here, so we know that we're traveling at 33 1/3 RPMs, and we know what the average velocity of travel from the outside to the inside is going to be, maximum and minimum, we can pretty accurately calculate how wide that groove needs to be able to play a certain amount of time and to be able to reproduce the correct sound. So with that in mind, we can adjust how much velocity we need at low frequencies and how much velocity we need at higher frequencies. And by averaging that, and that's called pre-emphasis, okay, by changing that at those frequencies, we can make that entire set of frequencies fit in the same width no matter what. And that's what RIAA equalization is. It's a standard that was developed in order to overcome that problem. And it's basically it centers around a knee point of about 1 kilohertz. So 1 kilohertz, you're not cutting or boosting any of the frequencies. It's flat. Whatever you're feeding in is what's going on to the groove. When you get above 1 kilohertz, it'll start to cut the frequency down a little bit. Or I'm sorry, it'll start to boost the frequency up a little bit in the pre-emphasis. And at base frequencies below 1 kilohertz, it gradually starts to cut the amplitude a little bit so that you get pretty much the same width. Now, this is all about mechanical. Now, if we tried to play this back without undoing what we did, it would sound very tinny because the bass is cut really heavily and the treble is boosted and the mid-range is flat, and the song that you're listening to would sound nothing like it was originally recorded. So what we need to do is we need to return it back to normal. So once that stylus on your record player reads the information off of this, it has to boost those bass frequencies back up to normal and reduce those high frequencies back down to normal so that you get a flat frequency response. And that's what RIAA equalization is. And that's called, when we put that RIAA on, we call that pre-emphasis. And when we take the RIAA curve back off, we call that de-emphasis. And just like when we have to package something up before we ship it, you know, we squish it down and make it as small as possible so that it's the smallest package and it costs the least amount to ship. Same thing goes with the information we're putting on this record. We're packaging it to get it from the source into your amplifier, and then we're unpackaging it when it gets to your amplifier and returning it back to normal. That's what this is. So that's exactly what RIAA does. If any of you ever tried to just take a magnetic cartridge turntable and plug it into something that did not have a proper phono stage, you would rapidly find out that it doesn't sound very good. It sounds very tinny and shrill, and it doesn't sound right. That is why. So long story short, the cutting stylus on a record cutting lathe travels at a constant velocity, which makes it move a further distance back and forth at lower frequencies than it does at higher frequencies. And if that's the case, that means that the width of the groove would vary with low to high frequencies. And in order to make the groove a constant width, you have to compensate for that by lowering and raising the amplitude and the distance that cutting stylus travels based on frequency, low frequency versus high. And that's what RIAA equalization does. It's just a way to fit more information in a more efficient way onto the groove of the record. And de-emphasis is a way to return it back to its normal sound once you read it back off of the record with your record player. Hope that makes sense, because that's my best effort at being able to explain it. So, as a repair technician, here's your problem. If you want to test a phono stage in an amplifier, and you want to use for instance, your signal generator, it's not going to react properly because, of course, if you feed a constant amplitude signal into your phono stage from your signal generator, as you change the frequency, the amplitude coming out of the phono stage will change because of that RIAA de-emphasis. So what you have to do is you have to simulate what that record cutting lathe is doing by putting a simulated pre-emphasis onto your signal, whatever you do, before you feed it into your phonograph or into your phono input. And that's actually a lot simpler than you might think. All that you really need is a simple little filter network, which is right here. Now this is the standard filter network, and it's not perfect. It consists of 3 resistors and 2 capacitors, and you could actually build this, and just for the sake of testing your phono stage, it will work for the most part. Although it's not 100% perfect, it's close enough for just testing something on your bench. So if you wanted to get a little proto board and kind of hack these few parts together, you can't find an 883.3K resistor, but you can use a 910K, and it would be pretty close. Now there are more elaborate versions of this that use multiple combinations of resistors and capacitors and so forth to get precisely the exact curve into this circuit. And there's lots of information online how to design them, how to build them. They're very simple. But there's a couple of other problems with this simple design here. One is it doesn't take into account the amplitude of the device that you're feeding into it. So for instance, the output impedance and the sheer amplitude of a line stage signal, you know, like the output of your MP3 player or a tape deck or something like that, is much higher than your phono stage. Your phono stage has way too much gain for that. So you need to compensate for that. And second of all, there are 2 different types of phono impedance and phono gains. One being for a moving magnet cartridge and one being for a moving coil cartridge. they both have different impedances and they both have different voltage outputs. So you need to put a little bit of extra attenuation circuitry in the front here to compensate for that, which is still not that complicated. But if you don't feel like designing all this mathematically or going online and trying to build something complicated, you have two other choices. Choice number one, which is the easy one, would be to go online and buy a pre-built RIAA, inverse RIAA module, which is this. And this is the one from Hagerman Labs, like I just showed you earlier. And this is just one of many that you can buy. And you can see this one even has variable attenuation, a -60 and a -40 dB. And you can switch it, and that compensates for whether you're connecting this to a moving magnet or a moving coil. So this is a really versatile little circuit. And you can see it uses a few more components to try to get that curve a little more accurate. Now the other one, which is the reason we're doing this video, is this little kit. And I know nothing about this other than I bought it on eBay from a, from just online. There were several vendors selling it. It was very inexpensive, and I thought I'd give it a try to see if it works. I'm sure it is going to be some variant of what we just saw. So with that in mind, we're going to build this, and then we're going to test it. And that's what the rest of this video will be about. So dumping the contents out of the little bag here, you can see there's not very many components to put together. And the main thing is this circuit board, and it looks pretty nice. You flip it over and it says Motronics Inverse 4. So I don't know what that means. But there it is if you want to stop the video and maybe take a picture of this if you're good at EagleCAD or KeyCAD or something and you want to print your own. Well, there it is. I don't know how visible that is because it's got some dark solder mask on it, but there you go. So you can see the little components, and again, this one I believe, yep, this one even has the attenuator for moving magnet and moving coil. So this is actually a really nice little kit, and it looks as if it pretty closely mimics the Hagerman. So let's start going through this and putting it together. So even though there's no instructions, this is really easy to assemble because they mark all the components right on the board. And all you have to do is go through, and if your eyes are good enough, you can look at the values. And let's see if I can see. That's a blue, gray, black, which appears to be 68 ohms. Is there a 68 ohm on there? Yeah, 68R. Right there. So we just, and no, I'm not using pliers and component forming thingies and all that. Don't need it. So I'm going to put that on there. Fold them over a little bit. Give them a little clip. Around the camera. And we solder it in. That one's a little bit too long. And there you go. Okay, so let me put the next one in. And there should be 2 of each resistor because this is a 2-channel. This is stereo. So, and there is glue on there. All right. And put the next one in. And again, if you're not good at your color codes, you can always use your ohm meter and just measure the resistance. or if your eyes can't see, like mine, a lot of times it's hard to see these little tiny bands on these tiny little 1/8 watt resistors. But that's okay. And we're going to just kind of fold the leads over a little bit to hold it and solder it in place. Okay. You're probably seeing this better than I am because I'm looking through this camera. All right, next. So let me put the rest of these resistors in so I don't bore you too badly, although this is probably more interesting than sitting at home being quarantined, I guess. So there's all of our resistors. Now a lot of you have asked me about circuitry and so forth for RIAA. And one of the things is there is no hard and fast circuit that you can use in a preamp that will give you the perfect RIAA equalization for de-emphasis. And the reason being is it depends on the design of your preamp stage. So the preamp can actually color the sound in some ways itself. And when you're adding that de-emphasis, you also have to take into consideration that the amount of coloration that your preamp puts into it, and you have to either add or subtract from that. So designing a phono stage is not as easy as just taking an op amp and applying a generic RIAA equalization filter to it, because there's a lot of factors that affect it. And while most people would not hear a difference if you get it close enough, if you're using a high-end set of speakers in a dedicated listening situation and a very good audio system, you will hear the difference, so that it becomes a little more critical. I'm not that critical of a listener, so but these, again, you can go all audiophile with this and have special board designed, and you can use super high precision components and get them to the exact amounts. You can go as crazy as you want with it. But if you just need to test it out to make sure it generally works, when you're to put something on you want to just connect your MP3 player to a phono stage to test it and say, yeah, it works, yes, it sounds okay, something like this will be more than sufficient. It'll work fine. I know there's always going to be people that'll say, they're junk or whatever. It's not. It just depends on what your purpose is. If you really want to be able to listen to a phono stage properly, connect a phonograph to it, not your MP3 player. This is just for testing purposes. So now let's put these, what are these? 1.8 nanofarad capacitors. And I think that's these blue ones. Yep, 182. So right there. So those are going to be your 1.8 nanofarads. We'll pop those in and flare them out a little bit. Give them a little snip. See, these are the kinds of things you resort to when you're quarantining yourself, huh? Just kind of get into this. All right. Next thing you know, you'll be hoarding toilet paper. I don't think people are hoarding toilet paper. I've come to the conclusion that with all of this government stimulus, the paper is being used to print all the extra money that they're printing. And once we're done with our stimulus program and the paper industry frees back up, I think toilet paper will be plentiful again. I'm messing around with you guys. So here we go. Okay, let's see if we can get these to fit. And these are the 6.8 nanofarad. And I don't have a schematic for this thing, of course. They didn't really give you anything other than a bag full of parts. So we're just going to have to see if this works. I bet you it does. And I don't remember what I paid for this, but I don't think it was expensive at all. As a matter of fact, I think it was extremely inexpensive. And again, you can get these on eBay. I'm sure they still sell them. All right, put this one in. A lot of people say, why are you even bothering with phonograph? It's terrible, you know, and there's always been debate over, you know, analog versus digital and vinyl versus digital and CD and all that sort of stuff. And I say whatever you like, you should listen to. Because it really doesn't matter what other people think. It matters what you think and what you enjoy. Some people, like myself, like the nostalgia of vinyl. There's just something, you know, good memories about it. And even though you do hear some crackles and pops sometimes or different things, without using, I don't even have to think in technical terms. I just, when I hear a record and it's played properly, it reminds me of the times when I used to listen to them, and I enjoy that sound. But we're all different, and that's okay. I can tell you that a lot of people, once they listen to vinyl, actually kind of begin to like it for a lot of the same reasons. And it's funny, a friend of mine who owns a very large record shop, and I know I've talked about them before, the Flipside Mall it's called, have seen quite the resurgence with younger people, with the younger generation, with an interest in vinyl. And I don't know why that is. Maybe it's just the nostalgia of it for them as well, even though they weren't around at the time. They just like the sound, and it's really neat to actually, it's kind of a mechanical device that you can kind of watch it working, and that's always interesting. But really, who knows why? I just know it's fun, so I'm going to keep doing it. So now let's see if we can figure out getting this little switch in here that's all bent up. That's one of the things, when they mail these, they kind of just throw them in a padded bag, and things can get bent up and whatnot. And who knows, maybe one day we'll get crazy and we'll design our own RIAA circuit that's a little more accurate, but that would just be a novelty item because I really don't need it. The only time I use these kinds of things is just to test and make sure it's working in general. If you want to evaluate an RIAA circuit in a phono stage on a system, you would need a very accurate one of these, and you would need very accurate signals to feed into it so that when you measure the output, you can tell if the de-emphasis circuit is working properly at all the different frequencies. There's even software for the computer that you can use to actually plot the curve of it. It'll sweep the frequencies into it and then read it back out through your sound card. I don't have that software, but I've seen things like that. And if you really get into this sort of hobby, that would be a good tool to be able to test this stuff. But for what we're doing, this will be good enough. So this is the ground right here, so you can actually attach a ground to your amplifier and to your source, kind of cut down on the hum. The one thing I wish this had was a little better mounting solution for mounting it. I don't even know what kind of job I'm doing here because I'm not looking very carefully, kind of behind the camera. And then we put the socket in there. And this is kind of neat. You can mount this with the little screw in the middle. So if you have a panel mount, you can cut it and so forth. But all right. So this is the trickiest part. I'm going to have to go off frame here, sorry. There we go. So we got that in there. No worries. And I have another, I ordered 2 of these when I got them because they were so cheap. So I have another one that I haven't built yet. But I know a lot of people ask about this all the time. I get emails about it. And every time I bring up phono stages and things, I get questions. So I thought I would do this. It would be interesting. Heck, we got nothing but time. At least I got nothing but time for right now. Some days it's really crazy at work here in the hospitals, but sometimes they just don't want us in there right now during this situation going on, because of all you have to go through to sign in and all the security things and health checks that you have to do. So we haven't been being called out for anything except emergency service lately, which is nice to get a break from it, but then after a while you're kind of ready to go back. So I'm really hoping this clears up soon. Really more for the people that are suffering from the illness. I don't want anybody to be sick, of course. So there we go. A completed RIAA reverse RIAA module. Inverse RIAA, as we call it. So now what we should be able to do is output, input. We should be able to connect our MP3 player right here, come out of here and go into the phono stage. And then we should be able to switch between magnetic and ceramic. Or I'm sorry, moving magnet and moving coil. Boy, oh boy. And try this out. So let's get our Lafayette back up on the bench and see if it works. So here it is connected up, and we have the output coming from our signal generator up there, going down into the module, and then it comes out of the module and goes around and goes into the phonograph input. And you can see I have phono selected, and I'm coming out of the tape record jacks of the preamp. In other words, I'm not using the speaker terminals because I don't want to go through the tone controls and all that of the amplifier. I want to just see when it comes out of the phono stage and into the line stage and out the record jacks. That's the most pure representation of what our phono stage is doing. Now, I have a sweep set on my signal generator. What's a sweep? Well, what it's doing is it's going to start at about 15 hertz and it's going to go up to about 30 kilohertz. So in theory, if this reverse or this inverse RIAA adapter module, and I hate when this camera does this, when the reverse RIAA module, if it's working properly, the amplitude should stay consistent the whole way across if I'm putting a consistent amplitude in. So let's go. And you saw a little bit at the lowest frequency, the amplitude was a little bit up, but I have it set so that it should stay between this line and this line the whole way. And you can see as we go from 10 hertz all the way up to 20 kilohertz, you can see just the tiniest little bit of shrinking, almost nothing. And for all intents and purposes, what we're doing, I think that's a pretty good, it's tracking pretty well. Again, if it were not working properly, so Well, let's just do that. Hold on a second. All right, take a look at this. We've removed the inverse RIAA adapter, and I just put a jumper in here. This is just a barrel connector. It just connects this connector to here. There's nothing in between here other than a jumper. It just connects the two ends together, makes it easier. And of course I had to lower the output of the signal generator a little bit because of I don't have the attenuation that this thing has either, so I have to compensate for that with my signal generator. So now I'm just putting out a 50 millivolt signal. But remember, this is a constant amplitude 50 millivolt signal. And watch what happens now when we do our frequency sweep. See what's happening? The higher the frequency, the lower the amplitude. What you're seeing right now is the influence of the RIAA equalization circuit in the phono stage of that amplifier. And there you go. And you can see there's channel 1 and channel 2. They're overlapping right now. So you can see they're tracking perfectly together. Now remember how they stayed flat in the same amplitude the whole way? And that's what our inverse RIAA circuit does. It allows us to check to make sure. Now, if there was a problem with the RIAA equalization of that phono stage, it would have done something like this, even with this in there. In other words, this would be flattening the curve. You know, it would be making a proper equalization curve. However, since it doesn't match the de-emphasis curve of the preamp, it would do this. It would change amplitude as you change frequency. But since it did not, we know that it was perfectly matched. So the inverse RIAA matched the RIAA de-emphasis of the preamp. So we know A, that this works, and we know B, that the preamp stage works properly. So just for comparison, we're going to use the commercially built Hagerman RIAA module and just see how it works. So let's get back onto the scope. And now when we turn our sweep on, you can see pretty flat. Although it did have a little bit of little more breathing at the low frequency. You could see just slightly, but not bad. So I'll tell you, that little cheap kit that we got from eBay, to me, looks like it works really well. Every bit as well or better than the Hagerman. He's got the same, pretty the same performance. So that's it. So I hope you enjoyed spending a little bit of time at the bench here. I know I did. That was fun. And now that we know that our phono stage is working properly, I guess we're ready to go on and check our quadraphonic. Now, I may have to do a little more research on this because there are a whole bunch of potentiometers on that SQ matrix module inside this receiver. Now, chances are they're all good and we won't have to touch it. But if we do need to make some adjustments, I'm not really sure how we're going to do it because there's no procedure in the book and there's not even a schematic for it in the book. So I'll have to go online and see if I can find a little more information before I go to the next video here. But we certainly know that it's definitely working and that it is, you know, at least the phono stage is working, and we should be able to work with this. I did have a very generous viewer upload from his Google Drive some test files that were encoded onto an MP3 file so that they can be played through this, and we should be able to decode them as SQ files when we go to test this. So thank you so much. You know who you are. I don't want to mention names for the sake of privacy, but thank you so much. Anyway, that's it for right now. I wish you all peace, joy, happiness, and good health. Obviously, good health in these times. And we'll be back soon. Take care. Bye-bye.